tables, try and get us prepped for this concept of mathematical induction. And it says respond to the following prompts in writing. I don't necessarily think that you have to write this down. I'm going to have you talk about it with your table groups. Know that there are not necessarily right or wrong answers that I'm looking for. It's more just like getting us thinking about this piece that's going to be important for mathematical induction. And these prompts are just meant to kind of get your thoughts and ideas about proofs before we start our work, because that's what mathematical induction is, proofs. So, here are, you're going to love this mathematical induction, it's so fun, okay? Here are my 3 questions that you should discuss with your table groups. What is proof to you? What activities or processes are involved in constructing proofs? And how do you know when you actually prove something? So go ahead, go at it, talk. I'm going to be eavesdropping on your conversations. And how do you know when Okay, let's come together, share some ideas. Can a group tell me what they said about what is proof? What does proof mean in math? Using evidence to prove a point, or maybe we would not use the word in the word make a point or something like that, right? State a point. I also heard people talking about justification, evidence, reasoning. Okay, so those things are involved with proof. What kind of activities or processes are involved in constructing a proof? What do you guys say for that? Lauren?
You always have a given, and then it's kind of like a chain from there. Like, once you find something, then that can lead to something else.
Okay, I like that. Yeah, start with the given and then follow the chain, and every step is going to lead to another step, and then all of a sudden, you have your proof, right? So, how do you know when you've proven something?
When you answer the question.
When you answer the question, you could work backwards. You know, you have to make sure in your proof, like not only do you have to get to that statement, that answer, but you also have to make sure that you don't have any holes up above, right? No gaps, no places for me to say, but if, right? So you got to make sure that's a solid proof, that you've got all the steps and justifications that you need. What did your proofs look like in geometry? The 2 columns. So some people might have talked about that for constructing proofs. You know, like if you go online and you like look for something mathematical and you're looking and you might stumble upon a mathematical proof, it's probably highly unlikely that it's going to look straight up like a geometry 2-column proof. I mean, those are kind of centered to just geometry learning and saying, like, make your statement, give a reason, make your statement, give a reason. You probably were exposed to some other types of proofs in geometry, maybe like flow charts where you had arrows that said you go to the next thing. Or did you ever see a paragraph proof where it's just like sentences and you had to fill in like with this theorem and then I can say these equals are equal, but they're sentences. Okay. So a lot of times if you're Googling or you're seeing a proof in a math textbook or something like that, it kind of looks more like a paragraph proof, more like statements, but then math is mixed in. So that's kind of what the proofs by induction are going to look like for us. You're going to feel like a real mathematician tomorrow when we write those proofs. It's going to be so fun. Okay, so you come up with your little mathematician name that you want to go by, and you'll be writing proofs up. It's going to be great. All right, we're going to talk real quickly about how proof by induction works. Okay, and it centers around the idea of the domino effect. So in dominoes, you know, if you set them up, we're not playing the game dominoes, we're lining up the dominoes. If you knock one down, the next one will fall, the next one will fall, the next one will fall. Okay, so I've got a nice little video for you to always remember the domino effect for your, wouldn't that be cool? On a mattress? They broke the Guinness Book of World Records. Then someone else broke it again, because why wouldn't you? I would be like so nervous, like, oh, no, I don't want to do it, someone take my spot. And then it will fall. I can't watch it because it makes me a little motion sick, so if you're like me, turn away.
Aren't they supposed to be working?
You gotta have a little fun, okay? Okay, so you just need to, when we talk about mathematical induction, you need to be thinking about that video, and this is your goal. On the next slide, we're going to talk about, you're going to prove the very first step, and then you're going to show that a step proves the step after that. So if you prove the first step, and then you prove that one before proves the one after, the first step's going to knock down the second's going to knock down the third, and you'll have your full domino effect. So you'll have proven it for all cases. Remember in geometry, you probably talked about a counterexample, okay, where you could like come up with an example that didn't work. Well, here we're going to show that there are no counterexamples. We're going to prove it for all the steps because they're going to knock each other down. And this follows from what we did right before Thanksgiving break. This follows directly after sequences and series. So our proofs tomorrow are actually going to be centered around series. So they're following the pattern, and we're showing that one term will knock the next term down, and so we prove the statement for all cases. Okay. So here you should write this next slide down in your notebooks, and we're going to refer to it tomorrow. Okay. It's the principle of mathematical induction. Okay. And when you read about or you see mathematical induction, you want to think about that domino effect. I want to show that I can knock down all the cases. Okay? And then I'll have proven it for every single one to infinity. Okay, so we're going to start by letting some p sub n be a statement about a positive integer n. Remember, this is building right off of sequences and series. So our p sub n's tomorrow are actually going to look like s sub n. So they're going to be like series statements. And when we say it's a statement involving a positive integer n, it's like an equation or an expression. P sub n equals something involving n plus 1. Okay, something like that. Here's what we want to do. Do two things. The first thing we want to do, I'm going to refer to as my base step. The base step is to prove that the very first case is true. It's important that your first case is true because that's the first domino you knock down. Okay, so prove the first domino falls. You prove that's true. Follow it up with an induction step. Okay, so what the induction step is, this is your domino step, right? Base step is knocking over the first domino. Induction step is showing that all the dominoes fall. Okay, so to show that all the dominoes fall, what we need to show is that for some piece of k, it will knock over piece of k plus 1. Because k and k plus 1 are right after each other. Okay. Then it doesn't matter if it's the first and the second domino, the third and the fourth domino, the infinity and the infinity plus 1 domino. Okay, they're knocking each other over. If we can prove that k always knocks over k plus 1, we prove that in all cases. Okay, and all the dominoes fall. Okay. So I'm going to draw for today because I want to stress that domino thought for you. I'm going to draw my little dominoes. And this is going to be my k domino. This would be k plus 1. This would be k plus 2, so on and so on, right? And if we have these two steps together, okay, if we show that the first domino, k, knocks over, it's going to knock over domino 2, which is going to knock over domino 3, and so it's just going to continue on forever. So we only need to show 2 things. Remember in geometry, you always started with that given statement. You'd make the statement and say given, and then you would do all the work to get to your proved statement. That's how you knew you ended the proof. Okay. We'll know we end the proof when we show the base and the induction step work. And so then we usually make this statement down here at the bottom. It's kind of like just a nice way to close our proof in mathematician speak. Then the statement P sub n must be true for all positive integers. Now notice there is some change of letter. So we start with a P sub n that involves a positive integer n. In the induction step, we're just going to kind of sub in k for n. That's just the normal thing to do so that we can say k is some integer n. If you wrote it in the same, it wouldn't be a really big deal. Okay, but we're going to switch from n to k's and then back to n's at the end. Okay, tomorrow we're going to revisit this, so I'm going to say, look back in your notes from yesterday. This is what we want to look at, and we're going to see the same thing on the slide tomorrow. And then we're actually going to do the induction step tomorrow. What we're going to do today is just work on setting up P sub k in the induction step and P sub k plus 1. We have to know what P sub k plus 1 is going to look like so that we know when we stop our proof. Just like you did in geometry because you got to the proved statement. When we get to P sub k plus 1, we're done. Okay. So, the next slide, you don't have to write anything down. It's just a reminder. Today, we're just going to find P sub k plus 1. It's going to be quick and easy. Tomorrow, we're actually going to do the meat of the proof. So, we're going to have to do the algebra after the P sub k plus 1 to make the proof. So, let's start. I'm going to give you some P sub k. Now, if this were a proof, it would probably start off with a P sub n, and it would be P sub n equals 6 over n plus 2. And then we would show in the base step that P sub 1 is true. And then in the induction step, we would switch over to P sub k. We would assume P sub k is true, the 6 over k plus 2. And we would want to show that P sub k plus 1 is true. So we need to know what P sub k plus 1 is. What do you think you might do to get P sub k plus 1 if you know P sub k? Okay, here it is. How will I get P sub k plus 1 if I have P sub k? Plug k plus 1 in for k. Yeah. 6 over P sub k would just be 6 over k plus 2. But now we're doing P sub k plus 1, so where k is, we're going to sub in k plus 1. I did the next term. And then in the denominator, can you simplify that a little bit? K plus 1 plus 2? Yeah, it would just be K plus 3. Great. So a piece of K plus 1 is 6 over K plus 3. That's my K plus 1 statement. So we're going to have to do that at the beginning of our induction step every time tomorrow. And then we'll actually do algebra after that to show that that is true. Okay, but we're not doing that today. So you're going to focus on this K sub 1 piece. Okay, let's do another one. P sub K equals 3 over K times K plus 4. We would like to find the piece of K plus 1. So I'll write that right over here. Piece of K plus 1 equals, in the numerator, just 3. In the denominator, anywhere I see K, I have to sub in K plus 1. So that would be K plus 1 times K plus 1 plus 4, which I should simplify that. That's just K plus 1 times K plus 5. And some of you might be saying, well, I could do K plus 5 without writing K plus 1 plus 4. Okay, cool. You don't have to write K plus 1 plus 4. Okay, so on the next slide, you could try that if you're feeling comfortable. Do I need you to FOIL this out? No. Okay, what I'm going to do, what you're going to see me do tomorrow in my proof, is when my algebra gets me to something quadratic, then I will factor it, and it will match piece of K plus 1. If you want to, in this step, FOIL that out and get a quadratic, K squared plus 6K plus 5, then when you do your math, if you do your algebra work, when you get to the quadratic, you don't have to factor. But I always just leave it in factored form, and then I factor in my algebra. Okay? So you don't have to multiply those things out. I'm going to give you 2 to try at your tables. You can see a little better. See if you can get the piece of K plus 1. And compare with the people around you if you need to. I'll put my answers up here in just a little bit. Do you agree? Not necessary for you to do any kind of expanding. I think it's probably easier to just factor the quadratics. They're obviously going to be like pretty simple quadratics to factor, right? So I just leave mine in the factored form, and then I'll just factor as necessary in my algebra. So what you're doing here is you are setting up for yourself so that you know what the K domino is, you know what the K plus 1 domino is, and you're going to show that k knocks over k plus 1. And then, like I said, it doesn't matter if it's second and third domino, 10th and 11th domino, 1000th and 1001 domino, they knock each other over. So your homework assignment, you've got about 9 minutes here. You can certainly get done. It's 6 questions. You're just setting up p sub k plus 1. So share a book, take a picture, write those down, get it done.